All right. So thank you so much for joining. Today we want to look at probability distributions as I've already indicated. And at the end of this course, you know that probability distributions are used to model problems and situations that involve uncertainty. Real life issues typically would involve extreme levels of uncertainties, right? So, um, how do you plan this year's, or how do you plan towards next year's meeting? How do you plan it this year? How do you plan electricity demand for next year so that doomsday doesn't appear? How do you plan for your cropping seasons when you don't even have any idea as to how the next, whether it's going to rain or it's going to shine or whatsoever is going to happen in the next season? So a lot of things would happen. Even those of you who do fantasy Premier League, you select your players in such a way that you don't even know whether the coach will feel the player you have selected, whether your player is going to score or not. Yet you have to make the decision today to meet an uncertain tomorrow. So if you triple captain Salah and he ends up not scoring or he ends up playing 2 minutes, that means that it is a problem for you, right? So these are some of the situations that we find ourselves that are uncertain, but we need to plan today to meet the uncertain tomorrow. And these things involve a lot of probabilities and all that we need to do. So basically, at the end of this section, you should be able to understand what you mean by random variables, what you mean by probability distributions, what the concept of random variable is. Okay, what you understand at the concept of random variables, and also you learn about discrete and continuous probability distributions. And the discrete, we are going to look at the binomial, the Poisson distribution, and the hypergeometric distributions. And we are going to compute probabilities and apply them in real world settings, and also identify which areas these places can be applied. So these are very important concepts for us to take note of, and we will gradually go through and see how best we can do. So this is your reading list. So we are going to really focus on the second book, the Anderson and Sweeney. You should try and get a copy of that book, and then just go through chapter 4 and 5, which has basically what we are doing today. Okay, so from business math, we did quite a number of lessons. For instance, we found out that probability is just a number, right, that lies between 0 and 1, and probabilities would usually measure the chance or the likelihood that an event would occur. We also learned that if you have an event that has a probability of 0, it just means that the event is not likely to occur. But if the event has a probability of 1, it means that the likelihood of that event occurring is very certain. And we did quite a number of computations and calculations as far as probabilities and statistics are concerned. It's quite well. We talked about the fact that an event with probability greater than 0 and less than 1 involves uncertainty. And we also learned that the closer it is to zero, the more unlikely it is, and then the closer it is to 1, the more likely that event is to occur. Right. We also talked about what an experiment is. We spoke about the sample space, and the experiment was about a means of generating outcomes. The sample space was about all the set of possible outcomes, right? So if you toss a coin once, then your sample space is either a head or a tail, right? If you toss a die once, your sample space is all numbers from 1 to 6, right? If you toss a coin 3 times, you have quite a larger sample space: head, 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 first toss, head, second toss, head, third toss, tail, and so on and so forth. So we had about 8 possible outcomes arising from that experiment. So we looked at that. And we also talked about an event. An event is basically a certain subset of the sample space, and mostly the event is what you, the researcher, or you, the one carrying out the experiment, are interested in, right? So these are some of the things that we looked at. we also discussed what a random variable is. Okay, I think my voice is okay. Is my voice okay now? We also discussed what a random variable is, right? And we define random variable to be a certain real valued function that is defined on a sample space, right? Basically, the random variable will just assign a value to an experiment, right? The set of outcomes in an experiment. So, for instance, if I toss a coin 3 times and I'm interested in events that the number of heads would occur. There can be no heads, there can be one head, there can be 2 heads, there can be 3 heads, right? And in this, the number of heads is a random variable that assumes the values from 0 to 3, okay? 0 to 3. And please, if you cannot hear me, I think you should do something with your volumes and your devices. Practically, I'm shouting here, so I don't think it is coming from me. But check your systems to see. But if anybody can hear me, I also want you to indicate that you can hear me. All right, let's go on. Okay, so there's another definition for random variables, right? For instance, I mean example, not necessarily definition. What grade do you anticipate to earn in UGBS 301? The grades could be anything from A to F, right? And if I assign 1 to A and 2 to B and so on and so forth until we get to F, where we assigned 7 to it, that means that your grades is a random variable that can assume any value from 1 to 7. So these are some of the things that we want to take note of. So that is a random variable. And there are 2 types of random variables. We learned all of this in 202, so this is just a revision from you, right? 2 types of random variable, 2 main types of random variables. The first one is what we term as a discrete random variable, and then second one is what we term as a continuous random variable. Now, in a discrete random variable, you have only a finite number of possible values. What do I mean by finite number of possible values? All I'm saying is that a discrete random variable would identify or would measure whole number values or assign whole number values to the random variables of interest. For instance, if I am asking you the number of cars or the number of students in a class, the number of students in a class could be a random variable. It can assume any number from 0 up to infinity, right? But I can never have 1.2 students, right? I have 5 students, 10 students, 15 students, 20 students. They are defined by a certain finite number of values, okay, and a certain whole number value. So the number of students in a class is a discrete random variable, right? The number of accidents that may occur is also a discrete random variable. But for a continuous random variable, the value can assume any number on the real line. Okay, so for instance, your salary or your height, I can have a height of 1.2 meters, and it will make sense, right? Or if my weight is 350.5 kilograms, that's about 7 cement bags. It can make sense. Okay, that is what we are talking about. Even when you add decimals and you even use irrational numbers to represent such a random variable, it still makes sense to whoever is listening to you. Okay, but for the discrete, there are certain random variables that will not necessarily make sense. So it's important that you differentiate between discrete and then continuous random variables. Every phenomenon or most phenomenon that we see or identify in lives, in business, in science, in every aspect of our lives can be modeled as a certain special type of random variable. Okay. And this random variable can either be discrete or continuous. Okay, and so there are various forms of discrete random variables, and then there are various forms of continuous random variables. And with time, we would identify what these things are. Okay, so let's take, for example, in 202, we talked about what a discrete random variables are, and I've already explained it, assuming a countable number of values. And there are certain examples that we can see. The number of times a 4 comes up in the roll of a die, right? The number of heads when a coin is tossed, say 4 times. You can never get 2.2 heads, right? So that gives you a discrete random variable situation that we have here. So these are some of the examples in for a discrete random variable. We can have discrete random variables with many possible outcomes. We can have discrete random variable that has only 2 outcomes, right? So a discrete random variable with a lot of outcomes could be the number of complaints in a day, right? The number of TVs in a household, the number of cars passing between 7 a.m. and 9 a.m. As we move on, I want you to give me some examples of discrete random variables. You can put them in the chat right now. The number of rings before a phone is answered. And then we can also have a discrete random variable with only 2 possible outcomes. So for instance, if I take gender biologically, right, it's either a male or female. If you are looking out for whether something is the quality of a product, the quality of a product can either be defective or non-defective. In a game, you can either win or lose, and probably you can also draw. Yeah, that's why, Lucille, that's why I talked about biologically. So I don't want us to move on to other things. Okay. Okay, so there are some examples that people have written. Let's look at it. Number of chairs in the classroom. Yes, that's a discrete random variable. Number of cars in Japan. Okay. Number of ones a die is no. What does it mean, Anthony? Number of ones a die is ruled. Probably you are talking about the number of time a one appears when a die is rolled, let's say 5 times or 6 times. Okay, the expression is very key. And the number of times you eat in a day, well, that could be a random variable that can assume figures from 1 to say 20, depending on who you are, right? So let's look at other examples of continuous random variables. So a continuous random variable can also assume any value on a continuum, right? It can either assume a certain, mostly uncountable number of values. For a thickness of an item, it could be measured as, let's say, 5.2 millimeters, 2.348 millimeters, the time required to take a task, the temperature of a solution, somebody's height in inches. What other examples can we have for continuous random variables? What other examples can we get? Yes, can anybody give us any example? You can put them in the chat as we move on. So as I said, continuous variable can assume any value on a continuum, and it can be expressed in decimal, in other numbers, rational and irrational numbers. It is just a collection of numbers on the real line. Yeah. So Anthony said weight, weight of what? Weight of a person, weight of an element. Okay, that's fine. But then, okay, the time an athlete takes to run a lap, the height of a person, yes, it's already here. Can it be a negative figure or just positive? That's a very interesting question. Yes, it can be a negative value, but as we move on to discuss, we go into details in probability, you would realize that mostly we'll be dealing with figures that are positive or minimum 0. Of course, if you are in debt, if your bank account is in debt, that means your account is really negative, right? So it's even negative. Or if you owe a lecturer some marks, that means that your raw score is already in negative, isn't it? So random variable, depending on how you express it, could either be negative or positive. Okay. Liters of water one can take in a day. That is also, yeah, that's great. What about age? Is age continuous or discrete? The age of a person, let me put it well. Is it continuous or discrete? Yes. Can anybody give us an answer? Is age continuous or discrete? And as usual, if you have a question, you can just put up your hand. I'll call you and then unmute you. Okay, Eunice says age is discrete. Monica says continuous. Ben says discrete. Free says discrete. Gerald says discrete. So discrete is winning. Okay, so let me call one of you. Eunice, why do you think age is discrete? Yeah. Why do you think age is discrete?
Yeah, so you can be a year old, 2, 3. I've not seen someone who is 3.5 years old. Or
there are people who are 3.5 and 4.5 years
yeah.
old. Okay, but when we are mentioning age as
I don't know how they calculate that,
okay,
but age should be a whole number. Yeah.
That's great. And somebody's hand is up. Anthony, yes, please, you can speak. Yeah.
So we can say when we are finding maybe the average age, maybe it could end up being in some form of age and a decimal. So it could assume both positions.
Yeah, but we are not talking about the average age. I think I asked a specific question about the age of a person. So it's not. I understand when you say the average age of people in a class. That could be. Yeah, that one we understand that it could have a lot of decimals. But if it is really the age of a person, Monica said it's continuous. Maybe we can hear from her. Monica, why do you think age is continuous?
I think it's continuous because we can consider the months on the whole year. So the months, let's say you are 3 years and then 6 months, you can say 3.5 years. Yeah.
Okay. All right. Thank you. So age can be described as a continuous random variable in a sense that if I am looking at my age actually in terms of how long have I really spent on this earth, right? Let's say I am 25 years, 11 months, 6 weeks, 3 weeks, and 2 days, and 5 hours, and 2 minutes old, right? All of those things can be expressed as decimals, the months, the weeks, and then the hours and the days that I've spent on this earth can be expressed as decimals. So largely you can express your age in a continuous format, but largely we've also discretized age, right? So that it's easier to mention. So until it's your birthday, we say I am 20 years until your 21st birthday that you jump into 21, isn't it? So yeah, it can be that confusing, but largely if I am looking at age as respects to the actual number of period of time you spent on earth, I can look at it in terms of the number of years you spend, the number of months, the number of weeks, the number of days, number of hours, minutes, and seconds, and counting. And if I'm expressing that in years, we can say that age becomes a continuous random variable. But I mean, the debate can continue, right? And so on and so forth. So we talked about probability distribution. We look at it as a way of describing uncertainties. We did all of this in UGBS 202 business math. That is if you still remember it, right? And mostly it can be placed in a graphical form. We also mentioned that we can express the probability distribution as the probability of all the possible outcomes within for a certain experiment, and we saw that the sum of what those possible outcomes would be 1. So there was an example, like if we are interested in the distribution of heads in 3 tosses of a coin. Yeah, if you look at that, there is the possibility of no heads, that's 1/8. Possibility of 1 head, that's 3/8. 2 heads, 3/8, and then 3 heads is also 1/8. And if you put all of these together, you get 1. That gives you a very legitimate probability distribution and random variable. Okay, this I've already explained. Probabilities can never be negative. Okay, please, again, if you are solving a question that relates to probability and supposed to find a probability, and you end up getting a negative answer, there's something wrong with your answer. So you should be able to go back and then check. And the sum of all possible outcomes would always be equal to 1. Okay, we talked about ways of summarizing probability distributions, and in UGBS 202 we looked at 2 main things: the mean, or the expectation, right, which is just the sum of the possible outcomes time the product of the possible outcomes and their respective probabilities, and then you put them together, and yeah, you have the mean. That gives you an idea of how the distribution is and some properties about the probability distribution. And then we also talked about the variance, right? The variance, which is also an indication of dispersion. We will go deep into that when we are doing these probability distributions proper. So we have some examples. Because of time, I wouldn't go deep into this example, but we've seen some of these examples that helped us to find the mean, the expectations, and then the variances of all that we wanted to do. Okay, so we want to move straight into what we are actually supposed to do for today, which is for us to look at the various forms of probability distributions. Before I move on, I will say that there are hundreds of probability distributions that are available in the world. You see, each period researchers come up with new distributions that fits certain phenomena that they want to describe. Okay, but we have a lot of quite a number of popular distributions, and it would have been fun for us to do all of these distributions, but this is not a probability class. This is a business math quantitative method class where we treat quite a wider range of topics. So we are going to really allow ourselves to do certain few probability distributions, and that are more applicable within our workspace and within the things that we do. And I believe that if you are quite serious with this, it can help you in one way or the other. So let's move on. So we want to first look at the discrete distributions. For discrete distributions, we'll be tackling 3 main probability distributions. First of all, we will look at what we call the binomial distribution. Then we will look at what we call the Poisson distribution, and then we would also look at what we call the hypergeometric distribution. And then we would also touch on the continuous random variables, where we will study what we call the normal distribution. Okay, so let's start with the binomial distribution. Okay, now there are a lot of things that we engage in this life, and there are several outcomes that come from our choices, right? But there are certain choices we make where the outcomes are only 2. Okay, so if we meet such situations, right, then we can model such a situation with a binomial distribution. So basically, a binomial distribution is used to describe a certain real world phenomena where, number 1, the events result in only 2 possible outcomes. Okay, and the event is repeated multiple times. So if the event is only done once, it's a special kind of distribution. We call it the Bernoulli distribution. We are not going to do that. But if the event is repeated multiple times and it results in two possible outcomes, then we have a binomial distribution. So we are going to describe a success, okay? I'm going to describe success in the series. And we are going to describe trials, and then I'm going to describe success. Please, in probability, success is not always how we describe success in society. So sometimes I may be interested in the number of defects in a certain lot of items. That's because I'm interested in number of defects. If I find a defective defective unit, I would indicate it as a success. Okay, but if I find a non-defective unit, I will indicate it as a failure. Okay, if I find a defective unit, I'll indicate it as a failure. If I find a non-defective unit, I'll indicate it as a failure. If I find a defective unit, I'll indicate it as a success. Okay, all right. So we are actually going to look at those situations. So those of you who are just joining, practically we are just starting our class. We are doing binomial distribution. What we've been doing for the past minutes has been recapping what you did in UGBS 202, right? So, which is quite, this one is a continuation of what we learned in 202. But basically, we are looking at what we call a binomial distribution. You've not missed much, so don't worry. What we call the binomial distribution, and the binomial distribution is what we are describing as the one that has only two outcomes. Okay, that phenomena that has only two outcomes, and these are the properties. The event results in two possible outcomes. The same event is repeated multiple times. Okay, and it just describes the distribution of successes in a series of trials. So some of the questions that we'll be asking is, let's say, out of n tries, what's the probability that X succeed? For instance, if I pick maybe a package that contains 20 items or 20 units of an item, how many of them are defective? Or what's the probability that I would obtain, let's say, 5 defective units or 10 defective units, and so on and so forth? That is the point of interest that we want to arrive at. That is what we are interested in. And the outcomes are either defective or non-defective. Okay, so those are the things. And these are some of the examples. A manufacturing plant labels items as either defective or non-defective, right? A firm bidding for a contract will either get the contract or not. So if I bid for, let's say, 5 contracts, okay, what's the probability that maybe I'll get 2 contracts, or I'll win 3 out of the contracts? Either you get it or not, there are 2 outcomes. A marketing firm will receive several responses of yes, I will buy, or no, I'll buy. New job applicants will either accept the offer or reject it, right? A guy can propose to about 5 ladies and waiting for their answers. What's the probability that the person will get maybe at least 1 acceptance or at least 1 bounce? Either you are accepted or your bounce can be 2 outcomes, right? And it can be modeled as a binomial distribution, even in this case. So these are real world issues and real world scenarios that can be modeled with a binomial distribution. Okay. Before we move on, can any other person give us an example of a situation that can be modeled as a binomial distribution? Quickly, in the next 1 minute, I think such an example can be given. Okay. Before we continue. Yes. Yes, Eugenia, you raised your hand. Yes, Eugenia, you can talk.
Sir, please, the chances of a student passing or failing his or her exam.
Yeah, so the pass of failing an exam could be a binomial distribution. And if you have multiple outcomes, multiple experiments, let's say, so this time, let's say that like your typical CA that you guys write, there are a lot of papers that you write. So if I write, let's say 3 papers or 4 papers, what's the probability that I pass, let's say 1, or I pass 2, or I pass 3? Because there are only 2 outcomes, either I pass or I fail, that can be modeled as a binomial distribution, right? Esther?
The chances that it would rain or not on a particular number of days.
Yeah, so on a certain number of days, the chances that it would rain or not can be modeled as a binomial distribution. Thank you so much. All right, I've seen some other responses here, and let's see. And someone says, whether you graduate or not, how can that be? Because that is just one outcome, one experiment. That would be more like a Bernoulli distribution, right? Abuaji, I'm not going to say what you wrote. Okay, the chance of getting head in a coin toss so you are getting, let's say, a head in certain multiple tosses of a coin. So what you should take note is that most of the answers you are giving here relates to only one experiment. Okay, but one thing that you should take note of, so Yeboah said whether you should marry me or not. One thing that you should take note of is that the event is repeated multiple times. The same event is repeated multiple times. So the same experiment is repeated multiple times. So if you see, when I think Esther was giving her answer, he was saying that whether it will rain for a certain number of days. So I have 5 days. What are the probabilities that it will rain, let's say, for 2 days out of the 5 days? What are the probabilities that among all the days, all the time, it rained? Okay, so we look at it in terms of setting multiple repetitions or multiple runs of that same experiment with that same set of possible outcomes. So if Yeboah, you decide that because your mouth may be as blunt as, let's say, disposable knife, so you are not so sure of winning the proposal of only one lady, and as a result you want to propose like 5 ladies at a time, that is 5 experiments that have been repeated, or experiment that will be repeated 5 times. So your outcome, you can get 1 acceptance only. There's an outcome that all the 5 will accept. There's the possibility that 3 would accept, and there's also the possibility that nobody will accept, right? So when you are dealing with binomial distribution, you should also be take note, right, of the fact that that same experiment is repeated multiple times. Okay, let's look at a roulette gambler. Well, that's also a good one. Okay, so these are the characteristics. So the trial has only 2 possible outcomes: success or failure, or yes or no, right? And then there is a fixed number, as I said, of n, and the trial should be what? Identical. And the trials of the experiment are independent of each other. So the results of experiment 1 shouldn't depend, or the outcome of experiment 2 shouldn't depend on what happened in experiment 1. Then we are interested in this. Now, please, this is where the mathematics come in. If you've never paid attention from the beginning of the class, this is where you pay attention, right? So the probability of success, P, remains constant from trial to trial. Okay, the probability of success will remain constant from trial to trial. And if P is a probability of success, then of course 1 minus P is the probability of failure. Now I want to ask a question. If an experiment has 2 outcomes, what do you think will be the probability of success? If an experiment has only 2 outcomes, what would you think will be the probability of success, or the probability of one event occurring? Is it even known with certainty if an experiment has 2 outcomes? Yes, anybody, you can raise your hand and answer, or you can indicate. Okay, so somebody's hand is up. Okay, Esther. All right.
I think that it would be the 1 minus the number of failures.
Okay, so I was asking if, so let's say that the probability of finding a defective item, right? Is it known with certainty? It's either defective or non-defective, right? So can you tell the
Yes.
probability of defective?
Yes.
What would be the probability of defective?
That'll be 1/2.
1/2. How did you get 1/2?
Because there are 2 results in the events,
Okay. Okay.
it will be either this or that. So if it is just 1, there will be 1 over the total number of possible results.
Okay. All right. Now let me use another example. Let's say that Real Madrid is playing a match with a third division team in Ghana, right? What's the chance that Real Madrid will win? Is it half? Or does Real Madrid have a higher chance of winning than the third division local team having a chance of winning? So basically, all I want to stress on here is that the fact that there are 2 outcomes doesn't necessarily mean that the probability of success would always be half. Okay, it is not always 1/2. Now, if I am pitching Real Madrid with another team which is of a very lower class, okay, and I look at the strength of these teams, I can say that, okay, Madrid has a higher chance of winning because they are more experienced and they have the more quality players, right? So perhaps the probability that Madrid will win could be 90% or 0.9, and the probability that they will lose will just be 10%. Okay, so these are some of the things that we are looking. But assuming that I'm pitching Real Madrid with a team at the same level where I can't really judge who would win, then I can say that maybe there's a 50-50 chance that maybe Madrid will win or maybe the other team would win. I hope you understand what I'm saying. So in the same way, for instance, I use Yeboah as an example, the guy who said, "Will you marry me or not?" Let's say that, I mean, he is one guy who is cool, he's calm, he's collected, he's tall, he has all that there is to get in a guy. When such a person proposes, right, and his mouth is as sharp as a two-edged sword, right? When such a person proposes, there's the higher chance that that person would receive an acceptance, right? But assuming your boy is the type that says, "Is your father around? Does your father have a dog? Have you eaten? Have you drank?" Okay. Those kind of conversation killers that happen on social media, right? And his mouth is quite blunt, like, let's say, disposable knife. For such a person, the probability that he gets accepted will be quite low. Okay, so the probability of a success is not necessarily grounded in the fact that it's either yes or it's either half or not. It's not half necessarily, but it depends on a lot of characteristics of the experiment and the outcomes and which outcome is more likely to occur. So you can have an experiment that has a probability of, say, more than half, okay, and you can have another outcome that has a probability of less than half occurring. So please let's take note of that. Okay, so yeah, but I'm sorry I use it as an example. Okay, yeah, it's just for this class. I don't know how sharp your mouth is. Okay, so let's take an example of what we can do, and please, you would be receiving quite story type examples, and you have to figure out what probability distribution it is. Okay, so let's take this example. Household Security produces and installs 300 custom-made home security units every week. The units are priced to include one-day installation service by 2 technicians. A unit with either a design or production problem must be modified on site and require more than 1 day to install. A lot of things. Household Security has completed an extensive study of its design and manufacturing systems. Now, the information shows, now this is where the meat of the question is. The information shows that if the company is operating at standard quality, 10% of the security units will have problems, right? And will require more than a day to install. Now, yes, I'm not going to ask you which distribution it is because, of course, we are dealing with binomial distribution, so it is binomial distribution. But the question I'm going to ask is, why do you think this question is a binomial distribution? Yes, can anybody help out? How do you denote a probability less than half or more? Nancy, we would handle your question as you move on. You get to understand it better. Okay. So how do you see that this is a binomial distribution? Anybody to help me? Okay, Emmanuel. Let's see. Yes, Emmanuel, you can speak. Oh, was it Esther? Yeah. Okay. Yeah, your hand is up, so you can speak.
Oh, sorry. I didn't put it down for the last time.
Hello? Okay, I think the hand wasn't ready. Yeah, so someone said either, yeah, okay, calm down. Lucille said it could either have a problem or not. Yeah, said you could, yeah, if you want to talk, I said raise your hand and I can unmute you. Okay, so Emmanuel, if you want to talk, just let me see your hand up and then I'll be able to unmute you. Okay, so Emmanuel, you can talk. Yeah, Emmanuel, you can talk.
Okay, thank you.
Right.
Because I think it's a binomial distribution because first it has 2 chances. The event has 2 chances of occurring in the sense that it can either have a problem or may not have a problem. And they've given the probability to be 10% if it's for it to have problems, okay, and 90 for it not to have any problem. Mm-hmm. And also the event occurs multiple times in that it occurs 300 times within the week.
Very good. I think that's an excellent answer. So you see that the properties of the binomial distribution are at play here. Number 1, there's a probability of success, and we have defined our success as to whether there's a problem. Okay, so you are looking for the unit that have problems, and there are only 2 outcomes here. Either it have problems or they do not have problems. So 2 outcomes, you've defined the probability of success. And then you have the number of units, which is being described as 300 custom-made units. So it's not just about the fact that it has only 2 outcomes, okay, but the fact that each of the independent trials or each of the independent units can either have a problem or will not have a problem. All right, thank you very much, Emma, for this answer. Okay, Monica, your hand is up. Yes, you have a question?
Yes, please. So I want to find out whether binomial distribution is able to tell us what event is likely to happen, or it is actually telling us the extent to which that event is likely to happen.
Okay, so we are interested in a certain event, okay, happening.
Yeah.
So it tells you what is the chance that a particular event would occur. So assuming that I am writing an exam, okay, I may be interested in the fact that, okay, out of the 10 papers I'm writing, I'm interested in the number of passes I would obtain. So the event of interest here is the number of passes that you would obtain. So we actually describe a certain random variable of interest, the event of interest to you. Okay, you do not just put it in a vague form, but you identify a certain random variable of interest, and then you would work with it. That is how the binomial distribution works for now. So you move on, then you see what we mean from over here. Okay. So there are only two possible outcomes. The binomial distribution applies to this situation because the following conditions exist. Number one, there are only two possible outcomes when a unit is installed. It is either good or it is defective. Number two, so you realize that finding a defective unit will be considered a success. That is how we define our success. And success would occur when you would observe, or you see the outcome of interest, when you observe your outcome of interest, right? Number two, each unit is designed and made in the same way. That's why we talk about identical trials, okay? And then the outcome of whether it is good or defective or undefective is independent of whether the preceding unit was good or defective, right? Then we can talk about the probability of a defective unit, and it's the same from unit to unit. It's identical, they have the same probability of defectives, right? The probability of a good unit is actually Q1 minus P. That is also one that remains constant from unit to unit. So let's take note of this, okay? So to determine the likely cause of defects, whether design or manufacturing, the quality assurance group developed a plan for dismantling a random sample of 4 security units each week. So here you've chosen a random sample of 4 security units, right? That's the sample size is just about 4 out of 300, or 1.33 relative to the size of the population. We are not really going into that. But basically, let the number of defective units in the random variable be denoted as X. Okay, so this is let X represent the number of defective units. Let X represent the number of defective units in the random variable of interest. And remember that here we've picked how many? We've picked a sample of 4. So we are now interested in the number of defective units in the sample of 4. We have a lot size of 300. We can't destroy all of them and see whether it's defective or not, right? But we can just pick a sample. So we have a sample of 4 security units that we have picked from. And from there, we want to find the probability of obtaining defectives or non-defectives, right? Mm-hmm. So the question is this: what is the probability that there will be no defective units? What is the probability that there will be only 1 defective unit out of the 4? What is the probability that there will be 2 defective units? What is the probability that there will be 3 defective units? And then what is the probability that all the units could be defective? So what we are saying is that a unit can be defective or not, right? For them to determine whether the unit is defective or not, and this is just one thing that relates to this question, they have to dismantle a random sample of 4 security units, okay, to find out where the defect is coming from. Okay, now I have 300. I can't dismantle all of them. I mean, for the destructive nature of the experiment, that's why we sample. Okay, so if I am sampling, let's say 4 units, I have 4 units to check whether they are defective or not. Then it means that out of the units, I can either have no defective units, I can either have only 1 defect, I can have 2 defects, I can have 3 defects, and I can have all the units that I've sampled being defective. So the question that you'll be interested in is, what is the likelihood of obtaining no defect? What is the likelihood of obtaining only 1 defect? What is the likelihood of obtaining 2 defects, 3 defects, or 4 defects? Okay, those are the questions that we are interested in answering, okay, for this particular problem. So how do we navigate that? How do we answer questions of this nature? So let's take it one after the other, okay, and then let's see. We are going to go through what I will call, or what generally we will call, the brute force solution, and then we will look at a more simplified approach to handling this one. So, number one, first of all, you identify your variables. If you've been with me from business math up to quantitative methods and up to this week, you will know that variable identification is a very important thing to take note of when you are dealing with stuff like these. Okay, so let G be the units of the number of good, let's say, yeah, we are going to describe G as that the unit is good, okay, or it's not defective, and then D as the event that occurs when the unit is defective. J is the event that the unit is undefective or the unit is good. So the probability of obtaining one good item is what? Is 0.9, right? The probability that the out of the lot a randomly selected item is good is 0.9. So if out of four units or out of 4 samples, okay, the chances that I will get no defective will be this. The first should be not defective, the second should be undefective, the third should be undefective, and the fourth should be undefective. That means that all the 4 items that I select, all of them should be what? Undefective. Okay, and the multiplication law of probability says that if the events are independent, then you can easily multiply the probability of the events to have the intersection. So the probability of no defective will mean that the first sample I select should be undefective. The second sample I select should be undefective. The third sample I select should be undefective, and the last sample I select should also be undefective. Okay, that is how this should be. So while the probability the first is undefective is 0.9, second undefective is also 0.9, third undefective is also 0.9, and the last undefective is also 0.9. If you multiply them, is 0.9 to the fourth, and that is 0.6561. So basically, there is about a 65.6% chance that you do not have a defect in the lots of items that you would select. But let's look at the probability of obtaining exactly one defective. Now, for you to obtain exactly one defective, these are the possible outcomes. Either the first is undefective, the second is undefective, the third is undefective, and the last one is defective, right? Which can be described as this. Or the first is undefective, second is undefective, the third rather is defective, and the last is undefective. Or the first is undefective, but the second is defective, and the third and the last are undefective. Or the first is defective, and the rest of the 3 are undefective. So how do we do this? So it means that this is 0.9, 0.9, 0.9, and this is 0.1. You multiply 0.9, 0.9, 0.9, then we have 0.1. You multiply 0.9, 0.1 here, 0.9, 0.9, then you have 0.1 here, then 0.9, 0.9, 0.9. You put all of them together, and then you get your final answer and what you get. So the probability of one defective item will be this. When you put them together, you get 0.2916. That is a very simple way. So if I'm asking you what the probability that there will be 2 defectives, it's that same thinking. Okay, it's that same thinking. Here, you see that there was only one way to find no defective. All of them are good. There are 4 ways that you can find one defective. Good, 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 defective, good, good, defective, good, good, defective, good, good, and then defective, good, good, good. So that one too is here. Then there are 6 ways of finding 2 defectives. Either the first is good, the second is good, third is defective, last is defective. First is good, second is defective. So good, defective, good, defective, good, defective, defective, good. If you look at the set of possible outcome, there are 6 ways that you can find 2 defectives in there. So we have that. And then there are also 4 ways that you can find 3 defectives. That's if you're interested in that. And there's also only 1 way to find 1 defective item. So these things we can take that. Okay. All right. So, but how? I mean, assuming you have quite a large number of samples to deal with, going through this brute force approach would be very, very difficult, right? So, thankfully, we are going to use combinatorial analysis to do that. And that is big English, but we are just saying that we're going to use combinations, right, to do that. Some of us in school learned about combinations and then permutations, right? So basically, that is what we are going to do. Why are we only using 4 outcomes? Because we selected 4. We are not dealing with 4 outcomes. We are dealing with a sample of 4. Okay, we are dealing with a sample of 4. Each of the sample of 4 has 2 outcomes. That is what you should take note of. The sample size is 4, but within each of the sample points, each of them have 2 outcomes. So my question was that if I select 4 items and each of them can either be defective or good, then there's only one way of finding a good item. Either it's like all of them should be good. The first should be good, the second should be good, the third should be good, and then the last should be good. Can we choose any sample size? Okay, so with respect to a test or an exam or whatsoever, you will be given a sample size. Okay. With respect to an actual experiment, you would have to select your own sample based on the characteristics of your experiment. Okay. All right. So basically, that is what we have. Yeah. Okay. So combination, we are going to use the combination analysis to do this. The number of ways of picking X ordered outcomes from M possibilities. So we are going to use combinations there. How many times can we pick a certain number of ordered outcomes from a certain number of possibilities? And if this is how we write it, we have N, sometimes it's written as N combination X, right? Or N, then the X is here, and then the combination is, the C is actually a big M thing. It's also visible on your calculators, and you can see that. Those of you who are using the ES, you can see that. Those of you who are using the senior brother of ES, which is the FX Casio, you can also see that on your calculations. But basically, the combination is calculated as the N factorial divided by X factorial times N minus X factorial. That exclamation sign is what we term as factorial notation. And if I have, let's say, 3 factorial, okay, 3 factorial is basically 3 times 2 times 1. If I have 4 factorial, it's basically 4 times 3 times 3 times 2 times 1. So successively, you just reduce the numbers by 1 and then you multiply it until you get to 0, right? And then, so N factorial is just N minus 1, N minus 2 times N minus 3 until you get to 1. You just reduce it until you get to 1. And by definition, 0 factorial is 1. Okay, 0 factorial is 1. These things measure the number of ways you can arrange a certain set of items. Okay, we will not go deeply into combinatorial analysis. It's an interesting branch of statistics and yeah, that we will deal with. Okay, so let's move on. So this is what we are going to use in our analysis, and please take note of this. It's going to appear in the formula and all that. So all right, so let's look at the binomial distribution formula, and do not fret when you see this. Okay, so basically what we are saying is that assuming you have an experiment, okay, that was repeated n times, it has two outcomes. It has a probability of success p. Okay, I'm interested in random variable x, the number of successes, okay, or the number of outcomes that you are interested in. That probability is actually n factorial over x factorial times n minus x factorial. Then the probability of success raised to the power x, and then the probability of failure raised to the power n minus x. This first part of the relation can actually be reduced towards the n combination x, the one that we saw. Okay, and n combination x, as we saw in the previous slide. So given this relation, we can actually calculate or compute whatever probability that we are interested in as far as binomial distributions are concerned. Okay, so P of x is the probability of x successes in n trials. X is the number of successes, okay? And the success, as I already indicated, is defined as what we are looking for, okay? N minus x is the number of failures. And then n is the random sample size, the number of trials, as I indicated. P is the probability of success per trial, and Q is the probability of failure. And of course, 0 factorial is just 1 by definition. We will take an example, and then we will see how you can do it. Okay, so let's take an example, and then let's see how these calculations will go. So on the basis of past experience, the shop manager of ShopRite at Accra Mall estimates that the probability of a customer making a purchase when he or she enters a store is 0.3. Okay, the probability that you make a purchase in ShopRite when you enter is 0.3. It tells you the number of window shoppers you have. What is the probability that 2 of the next 3 customers will make a purchase? What's the probability that 2 of the next 3 customers will make a purchase? Okay, so this is a binomial distribution because number 1, there are 2 outcomes. Either he makes a purchase or the person doesn't make a purchase. And then we are looking at a sample of 3 customers, right? So basically, we say that let n or let x, let's start with the x. Let x be what? Be the number of customers who make a purchase. Okay, the number of customers who make a purchase. That's the random variable of interest that you are looking out for. Okay, now let's get our parameters right. What is n? N is the sample, which is what? 3. Okay, very good. And what is p? P is the probability of success, which is the probability that you would find somebody making a purchase. So that is 0.3. Okay. Of course, if P is 0.3, then Q would be 1 minus P, which is 0.7, right? Very good. Now, if that we are looking for the probability that 2 of 3 customers will make a purchase. We are looking at the probability that what X is equal to 2. Okay, that is important. Okay, so how do we solve this? Remember the relation we said, the probability of X is equal to n factorial over x factorial n minus f factorial, could be written conveniently as n combination x, then p to the x, and then q to the power n minus x, right? So with that in mind, let's try to solve this question. So the experiment can be described as a certain sequence of 3 identical trials. That's why it is a binomial distribution, right? 2 outcomes, either the customer makes a purchase or the customer does not make a purchase. And the probability that the customer will make a purchase is 0.3, and the probability that it will not make a purchase is 0.3. I think I have actually identified all of them here. And the purchase decision of each customer is independent. So we are saying that the probability of X, right? I think I should type it right now. So I think that the probability of X is equal to n combination X, and just excuse me for a second. I'll be with you in a moment. So what we are saying is this, and probability that n is equal to X is the same as n combination X and P, let's say raised to the power X, right? And then Q, or 1 minus P, raised to the power n minus X, right? So this is what we have. Then you're saying that n is equal to n is equal to 3, and P is equal to 0.3, and then Q is equal to 0.7, or 1 minus P, yeah, 0.7. So if I'm looking at the probability that X is equal to 2, then it's just 2 combination 3, right? And combination, so we have 3 combination 2. Okay, let me make this superscript. It makes the document more elegant, right? So 3 combination 2, and then we have 3 raised to the power P is 0.3. That will be raised to the power X, that is 2, and then 0.7, also raised to the power n minus X, so 3 minus 2, that is 1. So this is how we will solve it, and let me make a superscript so that, yeah. So we have this, and then we have that. So 3 combination 2, if you check your calculators, I think that would return, let me make this a subscript rather. That would return a number, I think 6, right? Or 3. Yeah, 3 combination 3 is 3. So basically when you solve it, you would be able to get your final answer from what we are saying. Okay. All right. Okay. Yeah, you can solve it without using the binomial distribution formula. Indeed, yeah, it's true. But in case where you have a large n, then it becomes more difficult solving it without using the binomial distribution formula. That is why we have to solve it beginning this way. So yeah. All right. So let's move on, and then you see. Okay. Let's take another question. Because of the time, I would end that binomial distribution, and then we'll continue another time with the remainder of the distributions. Okay, I hope that is okay. All right. So at UGBS, 30% of the students are majoring in finance. In a sample of 10 students, what the probability that exactly 3 of them are majoring in finance? So in a sample of 10 students, what the probability that at least 3 are majoring in finance? First, you want to look at exactly 3, and secondly, you want to look at least 3. They are 2 different things. Okay, so you're either measuring in finance or you're not measuring in finance, right? So we have a distribution, a binomial distribution, and we have a sample of 10. So you need to identify what your N is, what your P is, and what your Q is, right? So here, what's our N? Our N is 10. First, we are saying that, first we say that let X be the number of students majoring in finance, okay? Let X be the number of students majoring in finance. And then we have N, the sample size to be 10. The probability is 30%.3, so Q is still that. So the probability that three people are exactly 3 are majoring in finance will be what? Probability that X is equal to 3, right? So you have 10 combination 3, right? And then 0.3 raised to the power 3 and 0.7 raised to the power 10 minus 3, that gives us 7. So if you have your calculators, I think the answer, if you do it well, you should get 0.2668. Now, my next question is this. What's the probability that at least 3, how do we solve that problem? There are at least 3. How do you solve that problem? At least 3. What do you understand when we say what's the probability of at least 3? Yes, Emmanuel. Emmanuel, your hand has been up. Is it the first time, or your hand was just, I should lower it? Yeah, Michael. Yeah, Michael, you can speak.
Sir, please, at least 3 means 3 or more students.
3 or more students, right? So it could be.
It could be the probability from 3, 4, 5, 6, 7 to 10.
To 10, very much. So there is a bound, right? Very, very good. What about when I say not more than 3?
So means from 0 students, where the probability from 0, 1, and 2.
Not more than 3. So 3 will be inclusive.
And 3.
Very good. 0 to 3. So you see that for binomial distribution, 0 is inclusive, because there can be a situation where we have no students measuring in finance. Now, so at least 3 means that the probability that X is what? Is greater, probability that X is greater or equal to 3, isn't it? So it's either probability that X is 3 plus probability that X is 4 plus probability that X is 5 plus probability that X is what? 10. Okay, and that's a long thing. That means you have to put each of these into the binomial formula and then solve. Okay, but there's a simple way of doing this without going through all of this. What do you think we can do without going through all of these probabilities that we are adding? What do you think we can do? Yes, can anybody help us? What do you think we can do? Okay, so basically what we can do. Okay, oh, sorry, Anthony, your hand is up. Yes, I didn't see that. Yes, Anthony.
Okay, so what you can do is that we see the probability, the sum of all the probabilities should give us 1.
Yes.
So if we can choose the probability that is less and subtract from 1, we can see that from probability of 2 downwards, when we subtract from 1, we'll get the probability of X greater than 3.
Okay, okay. Monica, your hand was up. Let me hear from you also. Yeah.
I was going to say that we should find the probability of X being 3 or 2 or 1. And then when we subtract that from 1, we'll get the probability of at least 3.
Yeah, but you didn't bring the 0, you see.
0, sorry.
Yeah. So the same as 1 minus probability, right? The probability that X is equal to 0, right? So let me, what do I do? Yeah. So probability that x is 0, then probability that x is 1, then the probability that x is what, 2. 3 is not inclusive because 3 is already here. So we have that. Okay. So let's take note of those things and then we apply them accordingly. Because of time, I would want us to end here and then we continue tomorrow. I would meet you up and then we continue with the class. Please, if you have any other question, just take note of them and then I'll respond to them accordingly. Sorry about that. So tomorrow we will meet at the same time. Not 6:30, but we meet at 7:30, the normal class time. Eunice, you have a question?
Please. So please, I'm getting confused with the definition for P and Q.
Yeah.
If I'm right, hello, sir, please, can you hear me?
Yeah, I'm listening. I can hear you.
Yeah. So, sir, please, the definition for the P and Q. Yeah, if I got you right, you said the P is for yeah, kind of thing. The P is for the success.
Yes. Yeah.
That's yeah. That's the number of defective goods or something.
Yeah.
Yeah, and the Q is for the trial.
No, I didn't say that. So Q is the failure probability. So what I said is that if probability of defective is say 10%, okay, then the probability of non-defective will be what? 90%. How did I get the 90%? I just subtracted the 10% from 1. Do you get it? Because there are only 2 outcomes, you either have a failure or a success. Okay, so the outcomes helps you to know that, okay, I'm dealing with a success. Sorry, there are 2 outcomes. So it's either a success or it's a failure. Okay, I have identified my success to be the number of defectives and identify my failure to be the number of non-defectives. So if success occurs with a 10% probability, then the failure would occur with a 90% probability. The trials is the number of independent trials that we have. Okay, so we have a set of trials, which is the number of independent trials that we have. Then we have a probability of success and a probability of failure. Basically, that is what we have given this. So I want you to go through this session and then we will meet again tomorrow at 7:30